So I get to teach you about tangent and secant and cosecant and cotangent today. Those are the other functions. You already know about sine, cosine, and tangent. So we'll do a little bit of review of what you're supposed to know so far, but we're going to keep that part super short so I can keep the video overall super short. So first off, a quick review. This is the amplitude. This, notice both parts are not variables. Pi is not a variable. That part is the b. And I'm hoping you're getting now that the period is 2 pi over b. So the period of this function would be 2 pi over b, which is 3 pi. The pi's can cancel. The period of this would be 2/3. And I know it feels confusing that there's no pi there, but remember, pi is just a number, 3.14. So the period of this thing is it takes 2/3 to get it over with, between 0 and 2/3. Okay. All right, so let's get on to, let's say we were going to graph, just a second here, get my larger eraser. This one down here. My first step would be to look and say, oh, this one's got a, the highest it'll go instead of 1, it'll go to 2/7. Instead of -1, it'll go to -2/7. The negative in the front, that's not the amplitude. The negative makes me know that the cosine would flip. I'd always start by graphing regular cosine. So regular cosine starts at 1 and then goes down. It reaches its lowest point, goes back up. Okay, and this would be 2 pi, and this would be 0, and this would be pi. And this mark, which is halfway between pi and 2 pi, is 3 pi over 2. And then this one would be pi over 2. All right, so that's a quick reminder of the base look of cosine. And then I would want to renumber that x-axis because of this 1/4 right here. Why? Because that's affecting the horizontal, which affects these numbers here. Okay, so I would factor out that 1/4, and then I would have theta minus, and then what is pi over 2 once you divide it by 1/4? That's what it means to factor something out of something. If I divide by 1/4, that leaves me regular pi here. And pi over 2 divided by 1/4 is the same as pi over 2 times 4 over 1. And that's 4 divided by 2 is 2 pi. So that is 2 pi. And that tells me on this problem, the phase shift, which is this part, is minus 2 pi. How'd you get that again? I factored out the 1/4. And when you factor out something, you're really dividing it by that thing. That's this. And I changed it to flip and multiply. See why those top 20 skills keep coming in? Got to be able to factor, got to be able to know how to divide a fraction by a fraction. Otherwise, you have no hope on that one. All right, so let's just answer these parts. The amplitude was 2/7. The period was 2 pi over b. And our b term is 1/4. So it's 2 pi divided by 1/4, which is the same as times 4, which makes it 8 pi. Make that a different color. All right, then horizontal shift. The horizontal shift is also known as the phase shift, and that's that. We factored out the 1/4 and we realize it's right 2 pi. And the vertical shift, there is none. It would have been outside of the parentheses. It would have been, like a number out like here. That in this other problem, this one was a phase shift. But this one doesn't have, sorry, not a phase shift. It was a vertical shift. This one doesn't have a vertical shift because there was nothing on the outside there. All right, so that's a superpower review, 4 minutes of the old stuff. Now, tangent. First of all, you need to know what tangent is. Tangent is sine divided by cosine. Do you remember that? And the reason that matters is because if I were to graph sine, I just put that in the wrong spot. Hold on. If I were to graph sine over cosine, here is I'm going to actually graph cosine first. There's cosine. Notice the asymptotes that are pre-drawn in for tangent, that's where cosine is 0. So I'm just trying to show you why, instead of just saying memorize this, that pi over 2 is where the asymptotes of tangent are. It's because tangent is sine over cosine, and if cosine is 0, like it is right here and right here, then those are the moments, pi over 2 and 3 pi over 2, where tangent will have an asymptote. Okay, so now this is the part where if you didn't understand that, you can go back and rewatch the video if you want, but I need to move on. And so I need you to understand what the parent tangent graph looks like. So here we go. With the asymptotes drawn in there, and I showed you why, at pi over 2, this one's at 3 pi over 2, and back this way would be negative pi over 2. That's what tangent looks like. Okay, so couldn't it also be drawn here? Yeah, but now you're drawing a second period or a second complete cycle of tangent. So tangent is usually only graphed in this first spot because usually you don't need multiple copies of it. All right. Now, one thing that's important to know about tangent is it's a different period because it goes this far to complete a full cycle, which if you count it up, half of a pi plus another half of a pi makes 1 pi. So its period is pi. The other one's periods were 2 pi. Okay, that's tangent. Now, what if they do this to you? Well, first of all, you have to know what tangent is. So first you draw in tangent. Here's tangent. And then you would try to figure out, okay, what has changed? Well, tangent does go up and down 1 and negative 1. I never really talked much about the y-axis, but it goes up forever. So of course it passes past 1. And it goes down forever. So of course it passes negative 1. So then how do you describe its amplitude? Well, all we're going to ask you to do is to say the amplitude is 3. And then we can put a 3 right here. And actually, we don't even talk about this usually as an amplitude because that's like how high it goes. It's just a vertical stretch in this case. All right, so next is this number. And do you remember that there was always this period is 2 pi over b thing, except now we're in tangent. And so period, it isn't 2 pi over b, it's pi over b. Okay, so this one's period is pi over 4. And so normal tangent would have had asymptotes at pi over 2 and negative pi over 2. But this isn't normal tangent. So we take this number right here and we say, should that multiply everything by 4? Nope, because it's on the inside. It should multiply everything by 1/4. And so this has become now pi over 4 times 2 is 8. And this is pi over 8. And so those are our new asymptotes for this new function. Why did you say, Mr. Server, that the period would be pi over b, which is pi over 4? If the period's pi over 4, do you get there's half of it here, 1/8 of a pi, or pi over 8, and half of it here. So that makes 2 pi over 8, which is pi over 4, which is what the period is of this function. All right, this one's just too brutal for a first day on tangent, so we're going to pass over this and move on. Secant. Secant is completely different than tangent. Secant, whenever I graph secant, I'm always going to go and graph its sister function first. What is the sister for secant? Cosine. And so if I'm going to graph cosine, I'm going to say the cosine starts here and goes down to here. And I like to do my cosine in 4 parts. I don't know if you remember that. That's 2. This is 3. That's 4. That's my cosine graph. Remember, I'm not graphing secant right now. I'm graphing cosine. And why are you graphing cosine, Mr. Server? Because secant is 1 over cosine, and therefore, wherever cosine was 0, like here and here, secant is going to have asymptotes there, because secant can't exist when secant really is 1 over cosine. Whenever cosine would be 0, secant can't exist. All right, so hopefully you've got these spots memorized by now. 2 pi, pi, pi over 2, and 3 pi over 2. By the way, if you aren't taking notes right now, you should be. You should stop right now and take notes. This is just cosine, but I'm about to show you secant, and you're going to forget later what secant was. You'll be really happy you had some notes. All right, so since I showed you there's asymptotes here and here, why are there asymptotes there again? Because secant can't exist when its denominator, cosine, is 0. All right, so now it doesn't exist there or there. And here's what the secant graph actually looks like. All right, I'm going to then put another half of a loop up there and another half of a loop up here. If I just continued, it would kind of go in that direction. Okay, but I'm going to stop it right here because I just want to graph one period of secant. I could remove all that blue writing, and because that's just cosine. The red stuff that's left, the asymptotes and those loops, that's what secant looks like. All right, so I'm going to give you a better picture of secant. I'm going to go off my margin here and say, so again, this is something where I personally would always just sketch cosine. And then I would make secant right on its back. It's the sister function. And so wherever cosine was 0, there's asymptotes. And I could go like this. I could go like that, and I could go like this. But usually we cut it off right here and right here because that way we're only showing exactly one period of cosecant. Sorry, that's secant. Okay. Now, if I had to make some changes to that, like for instance, they said, oh, by the way, it is not a normal secant graph. Well, of course, we're going to do the stretches and things the same exact way. So here's where 2 pi is. Here's where pi is. Here's where 0 is. This is pi over 2. This is 3 pi over 2. You got to get those down. Now, the blue one, that's secant. What if they had asked me instead to graph 2 secant? Well, it's not that complicated. It used to go up to 1 and down to -1. So with this 2 secant of theta, this 2 here is saying, I want you to be double the amplitude. So that's a 2, and that's a -2. What if I change a number in here? If I threw a number in there like a 4, then that would mean I'd go through and multiply all these numbers by 1/4. Because of what we know about inside horizontal shrinks, we know that we should not trust that 4 and multiply everything by 4. We multiply everything by 1/4. Okay, so that's the basics of how secant works. Now let's get to cosecant, CSC. All right, this one, as you might expect, I'm going to graph it writing on its sister back again. The sister for cosecant is sine. All right, so I'm going to graph this one. I'm going to start with sine. And then once I've got sine graphed, I'm going to go to cosecant. Okay, so to graph sine, I told you at the beginning how important it would be to be able to just do this graph super quick. That's 2 pi, that's pi. That's pi over 2. Counting by pi over 2s, this is 1 pi over 2. This is 2 pi over 2 here. This is 3 pi over 2. Okay, and that's what sine looks like. But we're trying to graph cosecant. So now wherever, since cosecant, since it's 1 over sine of x, wherever sine of x is 0, which is these spots right here, there are asymptotes at those three spots. That spot, that spot, that spot. Okay, and now this rides on its sister's back. The black one, that's cosecant. Okay, so what if they said, oh, by the way, I want you to put a negative 1/2 in front? Well, we'll start with the 1/2. That just changes our height to, instead of being 1 and negative 1, it's going to be 1/2 and negative 1/2. How about that negative in the front? That is going to cost us to have to rewrite everything. So then this loop of the U right here is going to have to flip and go down here. That was a vertical reflection. And then this part that's at the bottom has to be up here. There we go. And this has a horizontal piece of the B term is pi. All right. Do you remember that little formula? The period is 2 pi over B, and our B in this case is pi. So our new period is, after these pi's cancel, our new period is just 2. What does that mean? That means that the pi is going to get canceled off everything. We're multiplying everything by 1 over pi, and therefore the pi is just going to get canceled and replaced with a 1. You multiplied by 1 over pi everywhere. All right, so that's cosecant, and what if we made some changes to cosecant? And last but not least is cotangent. Now, cotangent, this one's a little harder to describe how it's related to tangent. Everybody thinks that, if tangent just looks like this, I hope you remember this from just a minute ago. The tangent looked like this. And here is pi over 2, and here's negative pi over 2. Everybody just thinks you just have to flip it over to be cotangent. And that's kind of got an element of truth to it. It is going to look like that, but it's not going to be there. It's going to be somewhere else. Okay, it's going to be shifted over. All right, so cotangent, of course, is related to tangent. Regular tangent looks like this. If cotangent is 1 over that, do you get that at this spot where tangent is 0, it has to have an asymptote there? Okay, so I'm going to do my new graph in red here. There has to be an asymptote here. And wouldn't there have been another tangent like over here if I graphed more than one tangent? Yes, there would. And at that spot, it's also going to have an asymptote like that. That's why cotangent's asymptotes are where they are. All right, now I'm just going to clean it up and just graph cotangent for you. So there's an asymptote here at 0, and there's an asymptote here at pi. One of the reasons I know that is because I know tangent and cotangent both have a period of 1 pi. So if this is starting at 0, it's super simple. It's got to go over pi. Okay. All right. So if I'm going to make cotangent, it's not like tangent where it rises from left to right. It falls as we go from left to right. So it looks like that. If I wanted to be a little more advanced, I could say there's a spot here at 1 where it would cross, and then there's a spot here at -1 that it would go through. Okay, and those are the 3 key spots. And if this is halfway to pi, this must be pi over 2 then. And then that spot would be pi over 4, and this spot would be 1 pi over 4, 2 pi over 4, 3 pi over 4 right there. Okay, so that's what cotangent looks like. And of course, we can do all those things where, what if we say we want it to be 40 cotangent? Okay, if I was going to graph 40 cotangent, I would change this to 40 and this to -40. forgery there, huh? And then what if we put a number in here in front of the x? Like if I wanted to put it as pi over 2x, then pi over 2, I can change that to be multiplying by the reciprocal, because again, you don't trust it. You don't multiply by pi over 2. You'd multiply everything by the reciprocal. So I'm going to multiply everything by 2 over pi. Multiply this by 2 over pi. Multiply this by 2 over pi. And you multiply this last part by 2 over pi. So it's 2 over pi times pi over 4. So pi's cancel. Okay, what else do you need to know? We've learned how all the new graphs look. Tangent, secant, cosecant, and cotangent. And that was my goal for this video. And so I would recommend that you come to my session afterwards where we talk more about having you practice and having you do a few of these. But I'm going to be giving you your assignment here, and I would recommend that for your homework for today, that you do, I think you can do these two. I might show you how to set those up in our session. This one's a little bit of a stretch, but that one's just brutal, so we'll take that one out. Okay, so I'd like you to do those three. Do you remember sine of 2 theta? I told you to memorize it. Let's see if you remember what it is. If you have to, you can always look it up. You've got Google. And then I may get again a little bit of help on this when we start these together in our question and answer session. Here, I'd like you to do these three, and those are just over the top, so taking those out. And then this one, it seems really hard, but it really isn't. Here's a reminder. You know what sine does. Normal sine just goes up to 1 and down to -1. This one has been doubled, okay? And then they started with 3. Another way to think of the initial population is where t equals 0. And remember, if the most that this part can be right here, the sine part, if the most that can be is 1 and the lowest it could be is -1, that really helps you figure out your initial and largest and smallest populations of butterflies. All right, so you're assigned that last one too. And that's it. No more problems than that. Have a wonderful day.